What's up, guys? It's Mr. Bringle, and today we're going to be talking about acceleration math problems. And we're going to start by going through some of the equations and what the variables mean and um, when to use these equations. And then we're going to do a few practice problems, practice examples, and then you'll do the practice exercises on your own. So let's jump right into it here. So this equation right here is kind of your base acceleration equation. Actually, another way to write this would be like this. Acceleration is equal to the change in velocity over the change in time. So you've seen this before. We've talked about that. That's the base definition for acceleration, a change in velocity over change in time. Well, remember that change in velocity is final velocity minus initial velocity over the time interval. So if you rearrange that equation, it comes out looking like this over here. So this is our base equation for acceleration. Now, Vf is your final velocity, Vi is your initial velocity, and then obviously A is acceleration and T is time. So sometimes you will actually see this equation rearranged like this over here, where you have the initial velocity at the end. And if you see Vi, I always use Vi, a subscript I, for initial velocity, but sometimes you'll see the little O there, V null, the initial velocity. So don't get confused if you see that. It's the same thing. Okay. Now, I'll kind of go back and talk about when you use the equation, but this says, use the equation when you don't need the position of the object. And we'll want to talk about that with all the other equations together. So the second equation that we have does involve a change in position. So that's where, this first equation does not use change in position. So that's definitely a differentiator between those two. It still uses initial velocity, a time interval, and then 1/2 times the acceleration times the time interval squared. Okay, so make sure that you don't forget that squared. That's a common error on that equation right there. And then a lot of times you'll use this equation when the initial velocity is 0. So when that happens, this whole part gets canceled out, and you end up just having that the change in position is equal to 1/2 AT squared. And this equation obviously does not have the final velocity like the first one, so that is a differentiator there. It uses change in position, and it does not use the final velocity. And then the last one does use final velocity and a change in position, but this time it does not have time. So the first two equations have time. This one's final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the change in position. Okay. So a lot of times what I do is I number these equations in the classroom, 1, 2, and 3, and we kind of go through them step by step and figure out which one we want to use. There is an alternative way to kind of figure out and a process that I like to use. And what I like to do is I like to first look for the change in position, because if you have the change in position, or if you need it, like you have to solve for it, then you can immediately eliminate the first equation. If you don't have the change in position and you don't need to solve for it, then immediately you know that you use the first equation. Okay. So that's the first question you ask yourself. Does this problem involve a change in position? Meaning, do we either need it or do we have it? Okay. Then the second question that will end it is, do we need or have the time? If you have the time and a change in position, then you use the second equation. And if you do not have the time, but you do have a change in position, you use the third equation. So again, if I can go through that step by step and say, okay, do I need or do I have the change in position? If the answer is no, I use the first equation. If the answer is yes, then I choose between 2 and 3, and that is based on whether or not the equation has the time. So you can make it real simple like that. Change in position, then look for the time, and that will help you choose the correct equation every single time. But if you would rather look for final velocity to do the second equation, and time for the third equation, and position for the first equation, that's fine. It's just you're looking for 3 different things. If you always use that step-by-step process of look for change in position, then look for time, I find that most people have pretty good success with choosing the correct equation. So one thing to talk about here is that all of these equations, delta x, remember, is a horizontal change in position. So let's say that a problem is vertical, like something's falling or something was thrown up in the air. You could change delta x to delta y, which would just be vertical change in position. And then what we can do here, it's highlighted in purple here, but we can also substitute the letter G in for A. G is a constant it's called the acceleration due to gravity, which is the natural acceleration of an object when it's in free fall. So free fall is referring to either an object that's dropped or if you throw an object up in the air. Basically, the definition of free fall is that the only force acting on the object is gravity. So when we throw an object up in the air, it's constantly accelerating because gravity's pushing down on it, right? So that force causes it to accelerate. And when you drop something, it falls and speeds up because of gravity. So the acceleration that's caused by gravity is this constant g, and we are always going to use 10 meters per second squared for that. That will be kind of it's technically 9.81 meters per second squared, but it makes things a lot easier for calculations and general physics when we just use 10. So this is kind of an introduction to the equations that we'll be using, and in a second video I'll have some practice problems for you.